everyone, my name is Noora Siddiqui, and I am so excited to be here today to share with you how we at the Human Genome Sequencing Center Clinical Lab built a resilient and scalable clinical genomics pipeline in the AWS cloud for all of us. Now, before I begin that story, a little bit about myself. I like to describe myself as a life scientist by education, an engineer by profession, and an educator by passion. My background in the life sciences and as a researcher really has enabled me to help researchers in higher education and academic medicine really apply technology to their unique research use cases. I also love to serve as an educator and currently am one of 10 nationally recognized AWS education champions driving digital transformation in higher education and healthcare. And I am really happy to be here to share with you our Baylor College of Medicine success story. Now, we successfully validated, re-architected, and migrated our production clinical genomics pipeline to the AWS cloud in a matter of months. And I want to let you know how and why we did that. So let's begin with why. Now, why we do what we do in the clinical division of the HGSC. The answer to that question is that healthcare is not one size fits all. The same medicine that works well in one person might not work as well in the other. And two people living in the same environment may not have the same genetic disposition for developing a certain disease. So a lot of our work in the clinical lab works towards this idea of precision medicine. So it comes as no surprise that we were awarded a grant from the National Institutes of Health, known as All of Us, to contribute to this project known as All of Us. Now, All of Us is a super unique project in that it seeks to generate genetic data from 1 million individuals across the United States from diverse backgrounds. Now, this is one of the largest sequencing projects in the world. And this historic mega project will create research platforms with data centered around and powered by individuals who have not been historically included in biomedical research in the past. And as a sequencing center, we really provide the sequencing, which is the biology portion of this triad here. Let me try and move. There you go. So you can see this picture. We focus on the biology segment of this project. So we provide the whole genome sequencing for this project, and this is a little bit of a high-level overview of what the whole genome sequencing process really looks like. So we receive a sample of genomic DNA all the way on the left, and that sample is broken into pieces and loaded onto a laboratory machine known as a sequencer over here in the center. And the raw data from these sequencing machines has to go through a large volume of computational analyses, a lot of, server crunching, number crunching, algorithm magic to stitch together a puzzle to determine if there are any actionable mutations that can be annotated for clinical significance and sent to patients, doctors, geneticists. And when I refer to the bioinformatics pipeline, I'm really focusing in on this green portion of this slide here, all of the algorithm magic and number crunching that I spoke to earlier. And the big picture over here is that a single sample will produce hundreds of files. Like this is talking about 300 to 500 files per sample, which is over 150 gigs of data. So for a project like all of us that seeks to sequence 1 million individuals, this is petabytes and petabytes of patient information. And the scale of this was just absolutely profound for our center. Predictions in early 2019 projected that processing samples for this project alone would imply a scale up of 4 times the production workload of our center from any other time in its history. So we now have to, in the past, we had to quadruple our production capacity at the drop of a hat for a single project. Now, the challenges to this and the challenges to using our legacy architecture, our on-premise architecture, were many. But from a computational standpoint, the challenges could be broken down into 3 main issues: the problem of time, the problem of storage, and the problem of scalability. So since these are clinical samples, turnaround time is extremely important. And we wouldn't be able to process at the rate required for all of us using only local resources at the time. Adding the existing project requirements of our center to this all of us project would definitely clog the system and prevent timeliness. And with a project of this scale, we're talking petabytes of storage and lots of compute. And the hardware and human burden of, racking and stacking servers, archiving, unarchiving data, planning for how much hardware we would need, and predicting when we'd need those servers by was absolutely burdensome. And as you can imagine, the underlying problem for all of these is the problem of cost. So we decided to focus our efforts on the problem of time to start with. So in that effort, we began to evaluate different hardware and software-based pipeline accelerators for sequencing analysis. So this is just 3 of the technologies we compared with regards to time. And you can see that our in-house bioinformatic analysis pipeline took around 80 wall clock hours. And we also tried a CPU accelerated pipeline that brought us down to 27 hours. And then we tried the cloud implementation of Illumina's Dragon technology, which utilizes FPGAs under the hood. And this brought our bioinformatic analysis sample processing time down to 1 hour and change. So this is going from 80 hours to 1 hour and change. And I really credit the fact that we were even able to, POC this technology to the fact that we were able to very quickly use a implementation of Illumina's Dragon in the AWS cloud. And this takes advantage of these specialized instances in the cloud that was just hardware we didn't have access to on-premise. So this was exciting. 80 hours to 1 hour and change is really big. However, speed and power mean nothing without direction and control. So we really, as a clinical team, focus on accuracy and precision, as well as sensitivity. So we had to do a lot of work to see how we could improve and test the accuracy of this platform that we were utilizing in cloud. And this is some early data here. And, all you have to take from this is that this technology, which is the orange bars, ended up scoring better on precision, sensitivity, and F-measure after some work on our part to, refine command line parameters. And we arrived at a command line parameter set that fit our unique needs. And looking again at the three challenges associated with using our legacy architecture, we were able to say, or I was able to say, hey, we have solved the problem of time. By adopting Dragon as a platform and decreasing the time for analysis from alignment to variant calling, this entire bioinformatic pipeline, from 80 hours to an hour plus change. And because we were validating a cloud-based version of this technology within AWS, we were getting a hint of Amazon offerings such as S3 and EC2 and different instance types such as the FPGA-based F instance family that I referred to earlier. And I remember the exact moment, I was a junior engineer, and I remember the exact moment I was in a discussion with the group and I was able to say, well, I don't think this is a problem of cut and pasting a new technology or platform into our workflow. I think that this is, actually a problem of cloud versus not cloud, because with the data that I had and some of the estimates from EC2 and S3, I was able to say that, I can solve the problems of time, storage, and scalability by migrating to cloud. And thus, the Great Migration began. And I really love this quote. History in its broadest aspect is a record of man's migrations from one environment to another. So just a little overview or insight. In terms of timeline, it took us around 3 months to validate Dragon, and the total migration took around 6 months, but these two were kind of happening concurrently and overlapped. So the actual migration of our clinical genomics pipeline happened in around 3 months. And I want to mention that, while at the Human Genome Sequencing Center, we had previously won 2 BioIT worldwide awards for innovating with genomic projects running at scale in the cloud, this was the first time that we were building a solution from the ground up, infrastructure as code. And we had no expertise, cloud expertise on the team. And I was able to, as an entry-level programmer analyst, to really learn about cloud and how to implement different cloud technologies, different AWS services for our unique problem in a very short amount of time. So it was very daunting to begin, but we saw that Illumina and AWS had a quick start available that deployed the Dragon solution to the cloud. Now, if you're not familiar, quick starts are automated infrastructure as code deployments that follow best practices or the AWS well-architected framework in terms of security, availability, architecture in general. So I really, really studied this as a guide. And for those who are looking to break into cloud, I highly recommend going and perusing through the different quick starts that AWS has available for all sorts of industries. Now, studying this guide, I knew that it wasn't going to come close to being a viable solution for us, since we use tens and tens of other software components for quality control and reporting, other than just, the Dragon technology that I was talking about. However, I used this quick start, and this is just a picture that came, an architecture diagram that came packaged with the quick start. I used this as a guide, and I was able to learn about things like the networking architecture and how to make it secure, as well as, how to sort of set up the public and private subnets and also utilize this really key technology that I've highlighted in green here, known as AWS Batch. I really wanted to highlight this because compliance and security are paramount for clinical data. And being able to use this quick start and other white papers regarding HIPAA compliant projects running in the cloud was really imperative to the success of developing our own solution. So, we studied this architecture and decided on a similar one that was capable of scaling to handle our burst workloads. And through this process, we actually containerized and modularized a lot of our software. Now, this hadn't been done before, this is really because we had a very monolithic architecture that grew out of a large research environment. So migrating to cloud was kind of an impetus to break this up into sort of a microservices architecture. So I did containerize a lot of that software, and the benefits were far reaching, not just in terms of our cloud implementation or our cloud architecture. So we were also able to take advantage, I want to go back and just mention, we were able to take advantage of an AWS market construct known as spot instances and bid on servers as market prices fluctuate. And the cost efficiency of doing this and running all of these containers in the cloud was, absolutely remarkable. Now, one of the major questions we faced when building our solution in the cloud was, how do we automate and orchestrate our workflows? And the great thing about cloud is that there are many tools and ways to accomplish the same task. There's a lot of flexibility to build a solution that suits your unique needs. I looked at some of AWS serverless offerings, AWS Lambda, and a managed function known as step functions that orchestrates these workflows, state machines, that's the word I was looking for, that orchestrates these state machines, as well as different open source technologies that are compatible with the cloud. And in the end, we ended up going with an architecture that took advantage of these serverless functions. And here's a little bit about what our architecture looks like, just like a basic overview. And I'm really happy to say that the orchestration that came out of using AWS Lambda, the serverless technology, as well as Amazon Simple Notification Service was extremely cost effective. So it says up here that the workflow orchestration costs less than a coffee each month. And that's true. For upwards of 5,000 to 8,000 samples a month, this solution still costs less than a cup of coffee. Now, another powerful hallmark of the architecture here is that it's very decoupled. And again, it's microservices architecture. And what I want you to take away from this very complicated picture is that each of these pieces could be developed and scaled independently and deployed independently of the other. And excuse me, utilizing infrastructure as code has made our system resilient to failure and also extremely flexible. And we were significantly able to expand our serverless functions to, grow as different project requirements also grew. So we can add tens and tens of serverless functions and quickly hook them up to different software components and utilize the same architecture in the cloud. It lends itself very well to deployments and to development and future development. Now, our solution is a hybrid cloud solution, which implies that some things do happen on premise. So over here in this diagram, I have our on-premise data center indicated in blue, and everything happening in the cloud in this gray outlined box over here. And most of our data resides in Amazon S3, and actually, I'd say 99% of our data is in the Amazon cloud. It's just a very small amount of quality control metrics with this dotted line over here that we pull back onto our on-premises data center. And what I want to say here is it was really easy to incorporate or connect our cloud infrastructure with our local data center and laboratory information system, also known as LIMS, written over here. So the question I'm sure you all have is, did it scale? You know, we had deployed this architecture across multiple availability zones and ensured security and compliance controls were met. And we started off by using it in parallel to the existing on-premise pipeline, just as a testing mechanism. So we knew it scaled a little, but it wasn't until all of us samples finally came in that we saw the true nature of scale. So here's a graph to show you that when samples first came in 2020, we were getting around 1,000 samples a month. In the end of 2021, or by mid-2021, this quadrupled to 4,000 samples per month, a quadrupling. And I am happy to say that we did absolutely nothing to handle that quadrupling effect. What I mean is the auto-scaling capability and dynamic scalability of the environment was able to handle the now larger bursts without any effort from us. And in the current day, All of Us production in Baylor College of Medicine has reached almost 100,000 samples and counting. And we haven't done too much to modify our initial architecture. And, you know, I like to describe this as what the great inventor Ron Popeil said to describe the at-home rotisserie as really a system where we could set it and forget it. So I also want to highlight that the cost efficiency of our solution was helped by using those spot instances and coming up with a thorough tagging strategy prior to expanding our resources in the cloud. This is another thing that I would definitely recommend to people who are beginning their journey in the cloud, is really sit down and define your tagging strategy, because you know, we can use those tags to manage storage archival and cost breakdowns, as well as make cost predictions. So here is a little view of our Cost Explorer in AWS. And our goal was to be able to say we ran X number of Y jobs for Z project, and this is the cost. And we're not quite there, but thanks to the ability to tag resources, we're able to see very granularly that this, you know, little turquoise bar, this $14 over here, was one particular software component, for example, for one particular project, for one particular purpose. And we can even see it was run by one particular person. So this is just an amazing amount of visibility that came via our cloud migration. So to conclude, we really were able to show the strength of utilizing the AWS cloud for our unique use case. You know, looking at this before and after in terms of the problem of time, we were able to move from 80 hours for bioinformatic analysis to 2 hours just by using a technology and specialized hardware that is, you know, available more easily in the cloud. We can spin up an FPGA instance in a matter of seconds, but actually ordering that specialized hardware and racking and stacking it takes a lot more time. We also, in terms of scalability, started off with a limited number of servers and difficult calculations trying to predict how many we would need for this project. And now we have an automated, scaling across unlimited servers in the cloud. And we used to have a very complicated archival and unarchival of data system in terms of the challenge of storage. And now we automate lifecycle management of data so that it meets compliance requirements and also just jumps straight into Amazon's Glacier archival storage system for immense cost savings. So our cloud adoption really enhanced our clinical experience as well as our research experience. And I'm really happy to say that this success really gave us a sense that, we can approach projects with a cloud first mentality. And it has really lended itself to more projects than just all of us running at scale in the cloud in present day. I'm really grateful again to have shared our Baylor College of Medicine success story with you all. Thank you, and I will be around for questions if you have any.